Not that it wasn't a good morning until it was 05, but you know. All right, let's revisit some things and just remind ourselves of some stuff before we get on this combination circuit business again. So what is this? Series circuit. What are three things we know about a series circuit? Current is the same.
All your resistances add up to your total resistance.
At any point, right?
Yeah.
R2 equals R1 plus R2 plus R3, dot. And what else?
All the voltage drops add up to the total voltage.
Sum of VR1 plus VR2 plus VR3, dot, the total. So yeah, that holds true in any series circuit, those three things. And that also becomes part of the combination circuit. We'll look at that in just a second. But let's go to parallel first. What do we know about this parallel circuit?
The voltage is the same throughout.
Voltage for each parallel branch is the same. And when we say the same, it's not equal in value. It literally is the same. You know, this is 12 volts. But the 12 volts that this branch is seeing is the same 12 volts that this branch is seeing is the same 12 volts. So we can't say we've got 12, 12, and 12, 36. We've got 12, 12, and 12, and it's all the same 12. So in parallel, the voltage for each parallel branch is the same as the applied voltage in a simple or the branch voltage in a combination. All right, what else?
Current is gonna add up to total current.
Sum of branch currents equals I total. And what else?
Total resistance is gonna be less than the
That's a
least
good one.
resistance.
Take away the equal. I was going somewhere else with that. That's right. But back, just feel like squatting down. So 1 over R2 equals 1 over R1 plus 1 over R2 plus 1 over R3, dot. Okay. So we see some characteristics, and again, some of these are gonna carry over when we talk about the combination. All right. What is something we know about this circuit? It's combinational. All right, let me go ahead and number these resistors. Well, let's don't. Let's do this. What do we know about the sum of the voltage drops of this particular circuit?
On the add up to both sources.
The
Yeah.
series part's gonna add up to the voltage, so
Yeah.
the parallel stays.
So we would take series resistor 1 plus single, let's not say single, D drop across parallel R2 become a question mark?
It's money.
Obviously, all over again. So yeah, we can take this plus the drop across any one of these, because the drop across this guy is the same as this and this, plus this. So those three are gonna add up to source voltage. Always and forever. Anybody know something? Moving right along. What else? Current's gonna be same in this guy as this guy, right? Yep. Well, yes and no. Series resistors will have same current, which is what? Total, yeah. What about the current through these branches? Current through parallel branches will equal IT. So what we have is we've got some current trucking along through here. Make that black. We've got some current coming through here. It's here. Some amount goes this way. Some other amount goes here. Then it splits. And then some other amount goes here. And as they recombine, they add up to the total. So right here, we're gonna have the total of this one, this one, and this one. Right here, we're gonna have the total of the last two, and here we'll have just this total. But all that should add up to IT. Is there anything else we missed? So I think we've got the properties pretty much. Let's work some fairly simple ones, and then we'll get back to our regular scheduled charter.
You mean the torture?
So, we're gonna keep it really simple. We'll go 20 volts. Say R1, R2, R3. We'll go 20 ohms, 10 ohms, and 60 ohms. So, take a minute and let's work that one. And let's remember the rules before we get any further. The drop across R1 plus the drop across this parallel branch has got to equal 20 volts. The current through R1 is going to be the same as I total, but we split here, so the two currents, the current of R2 and the current of R3, are going to add up to I total. So there's some rules we know have got to exist because of what we talked about a few minutes ago. most heads up, so let's go ahead and work this. So what we've got is obviously a fairly simple combination circuit, series resistor R1, which we know will see full current, R2 and R3, which are gonna split that current, but they'll see the same voltage. And in fact, they're gonna see the same voltage minus whatever R1 is dropping from the source. So if R1 is dropping 5 volts, then they'll see 15. If R1 is dropping 7 volts, they'll see 13. So we know some kind of rules there. So the very first thing I did was redraw the circuit so we can kind of see it in this form. So we're going to go ahead and solve the R2, R3 parallel. That's going to be 600 divided by 70. That's going to be 8.57. So the equivalent of R2 and R3 is 8.57. They wrote y'all someone that wrote so. Well done. Probably because it's fairly enough. So what is our total resistance now? We got 28.57. We add the 20 because of what we learned a moment ago, or already knew a moment ago. We add up the resistances in a series circuit. We've simplified this down to a simple series circuit by solving that parallel branch. So we add those two together to get total current. Now that we have total resistance. Now that we have total resistance, what can we get? Total current. When we divide 20 divided by 28.57, that gives us 0.7. So 0.7 amps. Not much of a round here or there, because I got 3 zeros after that. All right, so if we look, we know that current in the simple series is 0.7 amps. So when we come back over here and apply that, we know R1 is seeing that full 0.7 amps because there's no other path. Once we leave the source, the only path is through R1. So we can safely say R1 is seeing 0.7 amps. Well, now that we have that, what can we figure for R1? Voltage drop. V is I times R, so 0.7. I can do that in my head. Yep, 14, plus somebody shouted it out, but I really couldn't do that in my head. So if we know we have 14 volts here, and we started with 20, what do we have here? 6 volts. Yeah, across here we have 6 volts. Again, this is the same 6 volts. It's just shared between the branch. We're applying a voltage across this point. So this point and that point are electrically the same, so is this. So it's the same 6 volts. But we can go ahead and populate our chart. So now that we know the voltages for each of those, we can calculate current, correct? So what is current is equal to E divided by R. So what is 6 divided by 10? Yep. And I can predict this one. I can say 0.1 because that's 0.7 minus 0.6. But I can also do the math. I can divide 6 by 60 and I'll get 0.1. So let's make sure all the rules that we know and love are checking out. If we take the voltage across R1, which is 14 volts, and the voltage across R2 and R3, which is 6 volts, and we add 14 plus 6, and I know this is elementary, but we get 20 volts, which is our applied voltage. So that seems to hold true. If we look at the current going through this first resistor, which is I total, that's 0.7 amps. When we get to R2, we have 0.6 amps of that going through this guy, which we know if we mathematically calculate it, we should have 0.1 amps going through that guy. And we did do that calculation, and if we add those two together, sure enough, they add up to I total, just as we thought they would. So, pretty easy when we remember our concepts and all that. So, if I'm backtrack a little bit here. Don't you wish life had that? How nice would that be? So, that way I don't have to redraw my table. Hopefully, anyway. Let's do this. Okay, that will be, this is R three, Virgo, that will be R four. Bless you. Bless you. All right, y'all have it out for a moment. Ma'am? Indeed.
Oh, yeah.
Good job.
Lucky job. truck or rubber ducks? It was obviously for some movie. I'm sure we didn't create that on our own. Or maybe it was something else that rhymed with that, I don't know. That's why you shouldn't drink cleaning products, I guess.
I know,
Yep.
I caught the yellow yesterday, I got
When you do, you have children like this.
I got that. My good, my good leg, my good, my good, afraid.
All right. Starting to hear chatter, none of that has ohms or amps. All right, so let's take a look. All we did was add a third parallel resistor. So we know a few things about this. We know total resistance should be less than what?
This amount.
Right, less than 10 ohms. So if we arrive at some value that's not less than 10 ohms, we did math incorrectly. We know that whatever R1 drops, the remainder is going to be across this parallel branch. So I redrew it over here, and then I redrew it to a simple series circuit. So we've got to find that equivalent resistance of R2, 3, and 4. We'll pop up the calculator. Which oddly enough is not down here. Here it is. And again, I like the reciprocal formula. So let's do 10, 60, and 20. So we'll say 10 reciprocal plus 60 reciprocal plus 20 reciprocal equals, and get the reciprocal of that. And by golly, we got 6 ohms. I wasn't playing, but hey, we'll take it. So the equivalent resistance over here is now 6 ohms. And that applies C4 because it's less than 10, so we can't be sure 100% positive that it's right, we just know that it's not incorrect by using that theory. So if we're right, what is our total resistance? Yeah, we added the 20 ohms of R1, this, excuse me, 6 ohms of that, and we arrive at 26 ohms. Now if we've got 20 volts and 26 ohms, what can we calculate?
The current
Total current, right? So we'll divide 20 volts divided by 26 ohms. That'll give us a current of 0.77. So we've got 0.77 amps. So what's happening is, straight down here, we've got 0.77 amps. Same is true here. But when we get to that branch, what happens to that current? It splits. It splits not 2 ways this time, but 3 ways. But the 0.77, part of it's going to go that way, part of it's going to come down the middle, and part of it's going to come back. But once it does that, so what's really happening is this current is splitting through all 3. So a better illustration, rather than that line bisecting that branch over there, would be this right here. So I'll attempt to somehow redraw that without making an entire mess. But it comes down through here and it does this little thing. Then when it gets through, we've got the 0.77. Anyway. Okay. So we know for a fact that R1 is seeing that full 0.77 amps. So we can go ahead and write that in R1. Well, now we've got 2 parts of our 3-piece puzzle that we're always looking for, so we can calculate what? Voltage drop across R1, right? And voltage, if I put the pen down, is equal to I times R. So if I say 0.77 times 20, that's 15.4. So we'll write that in. So what that means is this guy's dropping 15.4 volts. And it's happening here too. And it's happening here too. So what do we know about this branch?
It's getting 4.6 volts.
Yeah, we can take 20, subtract 15.4, we get 4.6 volts. So we know R2, R3, and R4 are all seeing that 4.6 volts. So we can write that from the voltage of each one. Now that we've got two parts of that three-piece puzzle, we can again calculate our current there. And we know it should add up to 0.77 amps. Did I do something wrong?
No.
Okay. I thought I had written something wrong. All right, so if we say 4.6 divided by 10, 0.46, yeah, should have been able to do that in my head. That's when you just use the calculator too long. I can't do this one in my head. Not gonna do it anyway. Divided by, probably not accurately either. 0.76. So notice the zero there. First, it looked like it might be too large of a value, but 0.06.
I rounded up to 7.
Okay, 77.
I actually rounded it up to 8.8.
Keep two
Okay,
decimal
0.08. That's two decimal places. That's what we say is really good to go. All right, so let's divide 4.6 divided by 20.
You did 46 instead of 4.6.
It's 0.2. Little cheating method when you accidentally type it in the calculator wrong. So if we add up 0.46, 0.08, and 0.23, we should be somewhere near 0.77. 6 and 8 is 14, 3 is 7, 4 is 7, and all gone. Spot on. So everything that we proved to be true or thought to be true has been proven. We know that the sum of the voltage drops across R1 in the branch equals our applied voltage. We know that the voltage, the current through R1 splits when it gets to this branch. The sum of the branches currents add up to the applied current or the total current. And we've proven that circuit. Okay,
Can I have one more then?
one more of them. Just like this one.
I just caught it, so it's just like a.
I thought it got brighter in here.
Awesome.
All right, Chris.
I thought the coffee.
I did. Let me pick it in the old lady drink.
We'll get there, you eat glutton for punishment.
No, I said I had to, so I said I don't like it when you.
Okay, yeah, we'll get there though.
Are one of those go down the test?
Oh, yeah. Depends on how bored I am tonight.
You're not going to.
Need something to do.
Yeah.
I've caught up on our TV series, Netflix, got some else out. That's R4, not
Actually,
B4.
My brain's in overdrive.
Do
Energy drink.
100 ohms.
Overload, overdrive. That bunch of energy drinks and drink.
Yeah, that's the story of my, that's the story of my life with women right there. Dang. All right, there you go. Anytime I ask a girl on a date, that's what she always said. You said something. Which one of y'all wants to come explain this? It's Rick, I was talking to them,
Okay.
but hey, I don't mind.
Go ahead.
Cal will do it.
Oh, a selfish bone in my body.
All right.
Just all the same.
I know what I did. That's what I did.
calculate this parallel branch, it should be less than 10 ohms, or we've done something incorrect. Full current is gonna go through R1, it's gonna split at R2 and R3 and R4. The currents through R2, R3, and R4 should add up to the current through R1, which is current total. So, let's go ahead and solve our parallel branch. R2, 3, and 4 comes out to be what?
7.69.
7.69 ohms. So, if we've got 20 ohms in series with 7.69 ohms,
27.69.
yep. So now that we know total resistance and we know total voltage, we can whip out the old Casio or whatever it is we have. We can divide 200 divided by 27.69, and we get 7.22 amps, or we'll just simply round to 7.2 amps. Write that in red. So 7.2 amps of current is flowing here. And what we know true is this, it gets here, part of it goes this way, part of it goes this way, and part of it goes this way. But all three of those, once it comes out, we should add back up to, oops, not 0, 7.2 amps. So, what do we know about R1 as far as current?
Don't say the whole thing.
It's got the whole amount, so it's got the full 7.2 amps. Again, 2 parts of that 3-part puzzle. We can take I times R, which is 7.2, and we can multiply times 20.
You just did 7.
I did indeed. 7.2. These buttons are kind of hard to press. Times 20 equals 144 volts. So R1 is dropping 144 volts. Well, we can do some math and arrive at some conclusions. If we started with 200 volts, we're dropping 144 here. We can subtract that 144 drop, and we know what that parallel branch is seeing, which is 56 volts. So that means R2, R3, R4 are all seeing 56 volts. But again, we can whip out the trusty calculator. We can divide 56 by 100. I know. 0.56. And I did round a little bit. That's okay. Got that first one. So I can divide 56 by 50. Hey, I know that one too. And I can divide 56 by 10.
Hold on a minute. Go back and revisit R3 there, bro.
But if I have to instead of doubling it, didn't I? Try. See, I told you that's an easy one to do. So that would be 1.12 with. Sorry. That's what I get for not using a calculator and trying to use my brain this early morning. So let's actually do that for everybody's benefit. We divide 56 by 50. And we can do it right. 56 divided by 50 equals 1.12. I tried to get a little smart in my head and prove that I can't math, you get a little more. So let's add all those up, and we know those totals should add up close to 7.2. Again, I rounded to a single decimal point. Some of you guys may have did a double, that's perfectly fine. So let's do 5.60 plus 1.12 plus 0.56. That's 8, 6, 5, 11, it's 12. Carry 1, 7.28. I had 7.2. Somehow around me cost me 8 1/100 of the difference. Now, if I went 2 decimal places, probably would come out a lot more accurate than what it did. Still not too bad. Any of you want to give me $7.28 instead of $7.20? I'm game. Questions? Ready for the big dog? Let's kick it up a notch. We'll work slow. We'll do this one again, we'll break. All right, let's do votes. R1, R4, R2, R3, 5 ohms, 5 ohms, 10 ohms, 20 ohms. Here we go. No, R4 and R, I kinda got them near each other, but it's just like before. Okay. Probably just the way I wrote it inside instead of outside.
Nice.
No, I don't think so. It'll be very similar to your fruit test. From way back. Oh, you have a combination, I'm not sure. I don't think that'll be worded. Everything I think will have. Let's go back it. Now there may be something like, if you have a 10 ohm in parallel with a 50 ohm, which of these values could be the, possible answer to, or if your lowest value is 10 ohms, which of these could be, in parallel branch, which could be, obviously 15, couldn't be 12, couldn't be 11, couldn't be 8, could be. R2 is 10 ohms. Or it's either that or 10 occupied, I'm not sure what someone goes for Halloween, something. Push.
You get really simple numbers. No, more than that.
Yeah.
Alright, let's talk about this one for a minute. Before we even start solving values, let's think about things we know. The current through R1 and R4 is gonna be what?
Total current.
Total current. When current begins to go into the R2, R3 branch, what's gonna happen?
It's gonna split.
Split. So the sum of the current that's going in, or the sum of each branch equals that total current. So we're gonna see whatever total current is, it's gonna split different ways, but it's gonna equal to that total current. The sum of the voltage drops across R1, R4, and R2 and 3 are gonna equal what? Total voltage. And again, it's not R1 plus R2 plus R3 plus R4. It's R1 plus the voltage across R2 and R3 and R4. So don't add this twice, it's the same voltage source. So that's one of the things we have to keep in mind. So anyway, I've redrawn. We went down to our resistor, our parallel branch, R2, R3, R4. Then we're gonna solve this parallel branch and what is the equivalent resistance to 10 ohms and 20 ohms in parallel? 6.67 ohms. Now because we've got it laid out this way, we took it out, we see a simple series circuit, so what can I now do to get total resistance?
Total current.
Add them up, 5 and 5 is 10, plus 6.67, 16.67 ohms. Now that I have total voltage and total resistance, what can I do? Divide 50 volts, divided by 16.67, it's gonna give me pretty much 3 amps. So, I got 2.999. So, I got my total resistance by solving my parallel branch, adding all my resistances together, dividing that into 50 volts, and I got 3 amps. So, if I've got 3 amps coming down this line, we know that R1 is seeing that full 3 amps. When it gets here, it splits, but R4 is also seeing 3 amps. So let's go ahead and fill in R1, 3 amps, R4, 3 amps. Voltage is I times R, right? 3 times 5, I think I can do this without a calculator. 15. 3 times 5, 15. So what we're saying is we're dropping 15 volts here. We're dropping 15 volts here. And if we do it here, we're dropping 15 volts here. We're dropping 15 volts here. What are we dropping across the parallel branch?
20 volts.
20. We say 50 minus 15 is 35, minus another 15 is 20 volts. So we know R2 and R3 are dropping 20 volts each. So we'll go to R2, we'll populate 20. R3, we'll populate 20. Again, the same 20.
You said 20 volts each, which is the total.
Yeah, 20 volts total. 20 volts, the same 20 volts, yeah, that was bad wording on my part, thank you. So if I divide volts by resistance, I get current, so what's 20 divided by 10? What's 20 divided by 20? 1 amp. So let's see, 15 volts plus 20, again, they're not dropping 20 each, they're dropping 20, period, not 20 each. So 15 plus 20 is 35, plus 15 is 50, that equals our applied. We got 3 amps of current heading in, R2 is dropping 2, R3 is dropping 1, 2 plus 1 is 3, when they recombine, we've got 3 amps, and this circuit pretty well proves to be just like we thought it should. Question? We'll have some more. We're gonna kick up a little bit after this.
We need
Let's
to
see it.
we need to revisit,
We just learned something good.
we need to revisit two of them from yesterday, similar to them.
Parallel.
You want some parallels inside the parallel?
Yeah, that's what I'm having trouble with, is parallel inside the
We'll
parallel.
do some parallels. You have not because you have not.
You feel like your team's stuck right
Got a parallel and series with another.
Can I have a hundred some of these?
I'll do it.
Start booby trapping my shit.
You should do a PowerPoint on how she's unfair on power.
Me, and then she gonna email me. Don't tell me she sent it through plagiarism. I know mine wasn't plagiarism. I wrote my own stuff. He speak is, I know.
All right, I'll give you a few more minutes on this one, and then we'll talk about some things we know before we actually solve. And then we'll get from there. So let's see, let's set a hard time, 9:19, I'll go, 9:23. No pressure.
See what it is, I see it.
give it 2 more minutes. Let's see if you y'all still ciphering out there. Okay. Let's talk about some things first, before we even go to solving. Just remember, we can understand certain things about how the circuit works just based on some criteria we already know. How much current's going through R1? Well, all of it, right? Full current. When it gets to this junction, we're gonna get split, right? Some amount of current's gonna go this way, some amount's gonna go this way. So whatever this total current is gonna split here. Now when it gets to R2 and R3, we're gonna see another split. So let's just make an assumption, probably the wrong value, but let's say there's 5 amps of current going through R1, 3 amps go this way and 2 go that way. Well, that 3 amps is gonna split somewhere between R2 and R3, and the total will be 3 amps, but it might be 1.5, 1.5, it may be 2, 1, 1, 2, we don't know yet. But then when it recombines, it'll be 3. R4 will see that. This guy over here would see 2 amps, and when they recombine, they'd see the full 5 amps. The voltage across R5 is the same as the voltage across this point and that point. I don't even know what that is. Cool. So that's just there it is. So if I were to apply a voltmeter here and here, whatever voltage I read is going to be what's across R5, and it's also going to be across what's across R2 and R3 in parallel, and R4. Now this branch is going to drop some amount of voltage. This R4 is going to drop some amount of voltage. R2 and R3 will see the same value of that voltage. That value plus R4's value will equal whatever is across R5. Again, we know that. So just some little things we can take away and kind of understand about the circuit. I had to draw some of my draws down here on the bottom. So I redrew this pretty much like we did the first time, R1, then we branch off, go through R2 and R3 in parallel, then through R4 back to our source. Then in parallel with that was R5. So the first thing I did was solve this parallel branch within this parallel branch. And I came up with R2 and R3's equivalent value. That's in series with R4. So I have to solve that, and then I have to take those two values in parallel and do an equivalent for that. Now, I haven't done any of the calculations yet, but the very first thing I can do is go ahead and solve R2 in parallel with R3. That's going to be 600 divided by 50. That should be 12 ohms, right?
Where'd you get 600?
Oh, I did it wrong. R2 in parallel with R3. That's 20 times 30.
It was R2 and R3.
20
Right.
times 30.
Okay. So 20,
20 plus
30 equals 600 divided by 50 equals 12. Okay. So this guy, equivalent, is 12 ohms. Huh?
He didn't do it reciprocal, he did it product over some.
Oh, I did.
Yeah.
So that threw some of you, didn't it?
Yeah.
Okay, good.
Meal.
So I did product over some. When I do two, a lot of times I'll do it in my head. All I did was put the pen down. I did 20 times 30 equals, right, right. 20 times 30 equals, and then I divided that by 20 plus 30, which I could add in my head. So I got 12. Now I could have done reciprocal. Could have said 20 whatever x plus 30 whatever x equals whatever x, and got 12. So anyway, okay. Sorry, kind of threw everybody off, including me. So anyway, we know this R23 equivalent is 12 ohms. Correct. So we've gotten a little closer. So now,
That's the money, honey.
maybe I won the lottery. See y'all then. Now I've got a 12 ohm in series with R4, which is a 10 ohm. So what is this value? 22 ohms. So now I have a 22 ohm in parallel with a 20 ohm, I'm sorry. A 22 ohm in parallel with a 20 ohm. So what is my equivalent? Let's do it. Should be, yeah, somewhere close to half. So let's do it. We'll say 20 1 over x plus 22 1 over x equals 1 over x 10.48. Everybody with me there? So this is 10.48 ohms. R1 is 10 ohms. What do we now know?
Total resistance.
Total resistance. We can add the 10 and the 10.48, and we can get 20.48 ohms. So if we know total resistance, what can we now get? Total current, which is, yep, 60 divided by 20.48 equals 2.93 amps. Bless you. So let's go back to our redraws. So I've got 2.93 amps here. I've got the same thing here. And I've got the same here and here. So we can just kind of see as we go along. So what we see is we go back all the way to our original drawing. R1 is seeing all 2.93 amps. So let's go ahead and fill that in. So what can we get for R1? Yep, I times R would be 29.3. And I can do that hardly mathing. So let's come over here, and we know we've got 29.3 volts there. What's our total voltage? So what are we seeing across this branch? 30.7. Yes, across R2, R3, R4. We're seeing 30.7 here, and we're seeing 30.7 here. But it does us some good here, because R5 only is seeing that 30.7, right?
Right.
So we can go to R5, and we can say 30.7.
Wrong box, brother.
Wrong.
Ah.
Phone vote.
That was-
I didn't want to do that. Okay.
So R4 want to see that 30.72?
Well, R4 would see part of it. It's because R4, let's look right here, R5, if we put a meter here, we're gonna measure, or here, we're gonna measure 30.7 volts. If we put it here, we'll measure 30.7 volts. But if we put it here to here, we're gonna measure 30.7 minus whatever this guy dropped. Or if we put it here, we're gonna read 30.7 minus whatever that guy dropped. So we're gonna read some fraction of 30.7. So now that we have 30.7 volts, we can figure current through, R5 by dividing 30.7 divided by 20, right? That gives us 1.54 if we round. So let's look right here for a minute. We know up here we've got 2.93 amps, right?
Right.
We figured that. Through here, we have 1.54 amps. What does that tell us about this side over here?
You have to subtract what's going down R5.
Right. 2.93 minus 1.54 equals 1.39. So we've got 1.39 amps going through, splitting through this parallel branch, but fully going through R4.
R4, yeah.
So R4 is seeing a full 1.39 amps. So now that we know resistance and current, we can get the voltage drop just across R4, which is what? 13.9 volts. So here's what we know going back here. If we measured here to here, we had 30.7. R4 is dropping 13.9. What do we have across R2 and R3?
16.68.
16 point what? 16.8. So if we take 30.7 and we subtract 13.9, we now know what R2 and R3 are dropping. That's 16.8. Now we can just do some math. 16.8 divided by 20. 0.84. And 16.8 divided by 30. 0.56. So let's see if any of this makes sense as we travel our circuit. We started with 60 volts. R1 dropped 29.3. R5 dropped 30.7. We know that the combination of these two should equal 30.7. So R2 and R3 in parallel dropped 16.8. R4 dropped 13.9. And I can do some rough math there, and yeah, 30.7. So that works out right. So our voltage is calculated right. So let's look at current. For current, we have total current to be 2.93 amps. So I'll use green, we don't have much green to this one. So 2.93 amps is traveling through R1. So when it gets to this branch, we should see the sum of R2, R3, R4, and R5's current equal to 2.93. And I am slam out of board. But let's just run down to the calculator and put them in the calculator. So let's see if the current of R2, R3, R4, and R5 does indeed. So here is R2's 0.84 plus 0.56 plus 1.39 plus 1.5. Right, 0.84 plus 0.56 plus 1.39 plus 1.54. I can't math on the board. All right, one more time. 0.84 plus 0.56 plus, slow down, please, 1.39 plus
1.54.
it's not adding up, Calvin. let's think about this for a minute, I've done something wrong.
When you did that.
What did we do wrong?
Well,
Oh, we're doubling current.
yeah.
R2 has a current. Oh, we can only count the same current that's in R2 and R3 is what's in R4. So I can add R4 and R5, but I can't add R2 and R3 to it.
Right.
I can either add R2, R3 and R5, or I can add R4 and R5.
Okay.
That's where, so let's do the simple thing, let's add R4 and R5.
Okay.
1.39 plus 1.54, 2.93. Now we can go back and do the R2, R3, R5, should get the same thing. So 0.84 plus 0.56 plus 1.54, 2.94, little rounding issue there.
Yeah.
So, current gets here, some amount goes this way, some amount goes down this branch. The currents in R4 is the same current that splits through R2 and R3. So, we can only add R4's current and R5 to get total, or we can add R2, R3, and R5 to get the total. But we can't add them all, or we get too much. We could create a current multiplier, we'd be zero as well. Alright, let's get back to our regularly scheduled program. Let's see if we can find some that are somewhat safe. Fun time. Let's y'all want to go ahead and test. I heard you.
As long as you don't put those circuits like we just worked on there, I'll be good.
Okay. I mean, that right, that blew my
Yeah.
mind.
I got it right, but I see, I can't even help all sort of.
Then, okay. I was gonna say,
I was going along good and all of a
cause
sudden.
I went by the last drop. And number 4. And I had a issue. But we saw where our issue was fixed.
I didn't have, I had 2 before, and then we added 10. The total was 673.
Yeah.
It logged me out.
I don't think you got no internet.
Experiencing technical difficulties.
Yeah, mine.
Oh, awesome.
Yeah, we lost our internet.
Why don't we take a break? Kelly, what'd you do when you pulled that out? Did you like upset the entire?
The light up there blinked a little bit.
Yeah.
We probably had a surge.
Surge.
Knocked it out.
Okay, break time.
Ballast is going out in that load.
Oh, yeah.
R2 is 60, R4 is 15, R5 is 20.
R3 and R4 but they are here with
Should be close, unless you're around like 4.5 to 10. But it's gonna be a hair off. It's like the sheepdog told the farmer, said, I counted 30 sheep. The farmer said, I don't have 26. He said, that's okay, I rounded them up. I'll let you think about that one. About 3 more minutes. We've got to add 3 and 4 and get its value in series. And then we got to do the reciprocal of 2 and the series value of R3 and R4. Then you've got I saw the plane crash. Something like this.
It sucks with all my numbers.
So basically, you're kind of at two or three want to hit this.
Give me a couple more minutes on this, we're still working. Let's talk about some things we do know with this circuit. We know we got 120 volts applied to this circuit. We know that current is going to start, it's going to run through R1, it's going to get right here. So current's going to come here, it's going to go through R1, it's going to get right here, and we're going to have a split. We're going to have some current that goes this way, and we're going to have some current that goes this way. And then it's going to reunite. And then this last guy here is going to see full current once again. So we know this is IT, we know this is IT. We know that this plus that is IT. So we got all that pretty well down pat. All right, let's talk about some voltages now that we might not know. We know we have 120 volts. This guy's going to drop some amount of voltage. This guy is going to drop some amount of voltage. I forget I can change colors without changing skins. This guy is going to drop the remaining, which is going to be equal to the drop across these two. But we have to add this one and this one to equal that. So, we kind of got that down pat. So we've got our redraws up here. Let's take a look at what we did, and I want to make sure I know I haven't been really covering these redraws, but let's talk about how we did it. We left our source, and we go into R1. So we left our source, we went into R1. We get to a junction, so we can go through R2, then through R5, then through R5 to get back to our source. Let's come back to this junction where we split off to R2. We go through R3, R4, and R5 to get back to our source. R3, R4, and R5. And the top of R2 is electrically the same as the top of R3, R2, R3, R2, R3. The bottom of R4 is electrically the same as the bottom of R2, and both of those connect to R5. So we've got a pretty good redraw. And once we get it in this format, it's pretty easy to see. So what we've got here is we've got R1, we've got a parallel branch, but one of those branches has some series circuits in it. We've got to solve that series circuit in order to get to where we can solve that branch. And we have R5 in series with that. So when we look at this, we know a few things about current too. We know that current through R1 and current through R5 is IT. We talked about that a moment ago. And when we go through this branch, we're going to have some amount of that current go this way, and we're going to have some amount of that current go that way, and these two, that plus this, is going to equal IT. Right? Okay. So, oh, did not mean to do that. So we learned a valuable lesson about how to outdraw on our drawing. So we'll just leave it there, and hopefully we can work around it. So, let's take what we know now, and all I did was, once we got to the two single resistances, solve that down to a series resistor. All right, so now we've got to do R3 and 4 in series are 15 and a 5, so what does that add up to be? 20. So we'll write that in blue. So that's 20 ohms. And R2 is 60 ohms. So we've got to solve down 60 ohms and 20 ohms in parallel. We'll go about the calculator. We can do reciprocal, or we can do product over sum. 60 1 over x plus 20 1 over x equals 1 over x, 15 ohms. So now we have an equivalent for this guy of 15 ohms. R1 is 25 ohms. And R5 is 15, 20. I can't look sideways. So 25 plus 15 plus 20 is what? And that's our total resistance, right? Total equivalent resistance. So that's 60 ohms. So we now have voltage total, we have resistance total. What can we get? Current total, which is what? 2 amps, 120 volts. Remember back to our Ohm's law, 120 volts divided by 60 ohms gives us 2 amps. So let's look at our drawings. Here we've got 2 amps. Here we've got 2 amps. And between this split, whatever's going this way plus whatever's going that way, as I so eloquently drew here, has got to be 2 amps. So we got 2 amps going this way, 2 amps coming through here, and we've got a split in this parallel branch that we can't quite get yet. But we can go ahead and populate both R1 and R5 with 2 amps. So I times R gives us E or V. I sometimes interchange those two. So what is the voltage for R1? 2 times 25, we can do in our head, that's 50. 2 times 20, 40. All right, so now we know this guy, let's change the pen colors. We know this guy is dropping 50 volts. We know this guy is dropping 40 volts. So what do we know that we're going to measure out here?
30.
So if we put a meter here and here, we're going to measure 30 volts. Now that 30 volts is across both R3 and R4, and that same 30 volts is across R2. So now we've got the voltage across R2, right? So let's go ahead and write that before we lose sight of it, because when you're doing all this, it's easy to forget. So what can we go ahead and solve for now? So 30 volts divided by 60 ohms gives us 0 0.5 amps. All right, let's think about that for just a moment. Let's go back to here or here, it really doesn't matter. But we know we had 2 amps going this way. Through R2, 0.5 went this way. What's actually going on through R3 and R4? 1.5 amps, because we had 2 amps here, half an amp went that way, the other 1.5 amps has to go this way. And now we've got 2 pieces of that 3-part puzzle. I times R gives us E, so that's 5 times 1.5. What is 1.5 times 15? 22.5. Now let's go back and make sure these things that we think we knew are indeed true. All right, we had 50 volts supplied. We dropped 50 here, 40 here, and 30 across this parallel branch. 50 plus 40 plus 30 is 120. Now that 30 that's across R2, R3 and R4 should also total to 30. 22 and a half plus 7 and a half does total to 30. Okay, good there. 2 amps of current going through this guy, 2 amps going through here. We should be able to add the current through R2, the current through R3, 4, and get 2 amps. The current through R2 is half an amp, the current through R3 and R4, same current, is 1.5. So 0.5 plus 1.5 gives us 2. Everything we knew held true. All right. Number 9. This is going to be, we're not going to maybe be able to get everything, but we're going to be able to get some things here. So there may be some missing elements, but let's figure out as much as we possibly can. I'll tell you what, I'm going to throw one more piece in there that should be able to let me fill in the entire pie. With that, if I don't make you math wrong, I don't think that will. It should give you everything you could ever possibly want to know about that circuit. I'm gonna work one. In fact, I'll put some in now. Yep. What's the 2730? not give you enough. Don't lose it. We'll find out. Probably not, but we should be able to arrive at a few things. Should be able to arrive at a few things.
Literally fill out the chart, what's given.
Christian, what you did?
I stopped.
You did?
Yeah. I don't.
Make sure you give us total voltage instead of resistance.
We couldn't figure it out.
Did you get anything?
I got the
Resistance.
resistance
Figure it,
of,
give us the whole thing.
2 and 3.
The equivalent's the only thing you can figure out.
That's it.
The answer is 18, that's it.
He gave us the.
What's
total
the resistance
current.
of 2 and 3?
What?
The
He gave
total
us the
resistance of
total
2 and 4 is
current.
18.75, because they're reciprocal.
Or reciprocal?
Yeah, and then they're parallel, so they're
Oh.
reciprocal. That's all I got.
You need total voltage.
Yeah.
Or total current.
That's what I said, you gotta have it.
So did you multiply
Let's just
VGA?
work it with 100.
Right.
With how much voltage?
Oh, that's really high.
No. Memory.
Yeah, I'm still.
You ain't gonna look.
Answer's 42.
Answer's 42.
Yeah. Which answer?
Right, which one?
Oh, I'm sorry, that was the answer to life. There we go.
Big giant shoe. You ever seen the movie?
Don't ruin it for us.
Yeah. Ruined the movie for me, like, I went for this big giant.
Like when Jesus went for the Last Supper, he said, table for 26. He said, there's 13 of y'all. He said, we're all gonna sit on one side. You'll think about the portion of the Last Supper.
Oh, okay.
Let's see how much of this we can get. You said there's missing given all the information, especially if you work in manufacturing. All right, so we've got R1, R2, R3. All right, so we are given RT. We're given R1, R2, I should say, 25. R3, 75. We're given R1 is 20 volts. 20 volts. R4 is 30 volts. That's the exact.
That's all you got?
Okay. All right, let's try this. This might not work, but let's try it. Let's, try to make sure I don't screw this up. What can we solve for?
The equivalent of R2 and R3?
Equivalent of R2 and R3, which are what?
1.75.
18.75 volts. So if we do 25 in parallel with, ohms, I should say. 25 in parallel with, so let's redraw. R1, R2, R3. So there's R1, there's R2, there's R3, and R4. So we'll redraw once again. So this is R2, R3, it's 18.75 ohms. R1, we don't have a value there, but we do have 20 volts. R4, 30 volts. So we got R2, R3's equivalent, which we can't really put down because that doesn't go anywhere. So, let's do, I think they can finish that. Let's see if this screws up the situation any at all. 2 amps. My total is 2 amps. So give me just a minute. Let's go ahead and work. That way, if it doesn't work out, I don't have y'all wasting your time. So if R1's seeing 2 amps, we can go ahead and write that, right? That means R4 is also seeing 2 amps, correct? And then the parallel branch should be seeing the split of those two. So what is R4's resistance if it's 30 volts at 2 amps? 15 ohms. What is R1's resistance if it's 20 volts at 2 amps? 10. Let's see if mathematically that works. It does?
It doesn't.
Okay. Now let's just forget all about this problem. Apparently all we had to do is just solve that resistance. I'm not gonna lie, I stole these very quickly to throw in here, so I picked one with
Not enough information. And I suspect we're gonna have some savings. There it is. Well, then we definitely have some issues. Absolutely positively. We can say that without fail. However, but wait, there's more. Just like Billy May. There is that supposed to be easy when it's not easy.
Yeah, we did that one already, didn't we? Did we do that one?
I don't remember doing that.
Let's do that one. I mean, let's have fun doing this one.
You're gonna give us about an hour, right?
I will give you
Oh, that's easy.
2:45. So Cal, if you wanna follow us to the camera, obviously, 15 minutes of silence. Okay, let's take a look at this guy. Let's talk about some things here. We've got 5 volts going through or leaving out our circuit. We go through R1, it's gonna drop some amount. Then we reach a junction, we go through R2, R3, back to our supply. So go through R1, go through R2, R3, back to our supply. The other way, we go through R4, and then through R5 back to our supply, or R4 and through R8 back to our supply. So this redraw does stand true here. So we've got this circuit, so obviously we've got to solve this parallel branch within the parallel branch to move on. So my next draw had that solved down to a single value. And then we've got to add these two guys to get R2, R3 equivalent, add the R4, R5, and RA equivalent to get that one, and then we're down to our final 2 resistances there before we can get the total resistance. So let's take a look. R5 and RA in parallel are 4 ohms and 4 ohms. I don't even need a calculator if we remember. What does that give us for the equivalent resistance? 2 ohms, right? So over here, where R5 and RA are, we can write 2 ohms. That's 2 ohms. So now we've got the R4, R5 and RA. We know R4 is 10 ohms. And R2 is 4 ohms, R8 is 8 ohms, so 4 ohms, 8 ohms. So if we add the 4 and the 8, we get 12 ohms here. We add the 10 and the 2, we get 12 ohms here. What is 12 ohms and 12 ohms in parallel? 6 ohms. So the equivalent resistance of R2, R3, R4, R5, and RA is 6 ohms. And again, we did that just by taking R5 and RA, which were 4. If we do 4 times 4, if we do reciprocal, we're going to get 2. If we do product over sum, we're going to get 2. Either way, 16 divided by 8 gives us 2. So then, we got 10 plus 2 for 12, 4 plus 8 for 12. The equivalent of that, 12 times 12 is 144, divided by 24 will give us 6 ohms here. So 6 plus R1's value is 4 ohms, correct? R1 is 4 ohms. So what is 6 plus 4? 10. So our total resistance is what? 10 ohms. Well, if we've got 5 volts and we have 10 ohms, what is our total current? 0.5 amps. All right, so let's go back to our redraws. We can look at that. There's only one resistor that is getting full current. Which one is it? R1. R1 is seeing all 0.5 amps of current. So if we have, it's hard to see that dot. There we go. If we have half an amp, 4 ohms, what is voltage drop across R1? 2 volts, right? So if we come right here, write 2 volts, we can write 2 volts here. So what does it tell us about the voltage drop from here to here. If we measured right there, what would we measure? 3 volts, right? Okay, so we know there's 3 volts across this guy, there's 3 volts across this guy, and we know the current through both sides now. We know the total current. We know we got, what is our total current? 1/2 amp, right?
Yes.
All right, here's the tricky part. Is this branch and this branch equivalent? Current, resistance wise.
No.
Right here, 12 ohms, 12 ohms, right? So we know once we solve this right here, we've got an equivalent value of 12 ohms. What now?
So it's gonna be 0.25.
So let's think about this for a minute. We've got, I keep forgetting I have to change colors up here.
current's gonna split evenly between.
Current's gonna split evenly. We've got 0.5 amps coming down. We see the exact resistance on both sides. This branch is gonna see 0.25 amps. This branch is gonna see 0.25 amps because it's the same resistance value and they're equal resistances. So now we know 0.25, 0.25. Now, R2 is seeing all of the 0.25 amps, right? So we'll go ahead and write that in. Let's go ahead and keep going. R3 is seeing all 0.25 amps, right? R4 is seeing all 0.25 amps, right? Now, here's where it gets a little fun. When it hits here, we're going to split. So let's go back. We've done populated everything we know we can populate. I times R gives us voltage. So what is the voltage drop across R2? 1 volt. 2 volts. 8 times 0.25, 2.5 volts. Okay, let's examine this now that we've got it. All right, so we've got R4 seeing 2.5 volts right here, right? We've got R2 and R3 seeing how much voltage?
3 volts, so you got 3 in there.
So I've got 3 volts drop across R3, I've got 2.5 here. What is my drop across R5 and R8? 0.5 volts. So what is my current? 0.5 divided by 4. We'll whip out the old train.
12.5 million.
How much?
12.5 million.
0.125.
Or that.
Or that, yeah. Now, let's see if that holds true. The tricky part was we had an equivalent resistive branch. And if the resistive branch was equivalent, or it would split in half. That was the unknown possibly. So we have 5 volts. R1 right here is dropping 2 volts. And R2 and R3 are dropping 1 volt and 2 volts. 2 plus 1 plus 2 equals 5 volts. Now, we don't have to use those if we don't want to, because it should also work with the drop of this guy and this guy. So let's see. R4 is dropping 2.5 volts. R5 is dropping 0.5. And it really doesn't matter if we use R4, R5, or RA because they're equivalent. So 2, 2.5, 4.5 plus half volts 5, and you can get it over here, it'd be half a volt, that would be 5. So that holds true. So far, we're checking out. Current, oops, didn't this guy was 0.5 amps. So we know the current through these two plus the current through those. Wait, nope. So current gets here and split. Yeah, plus the current through this should equal half an amp, right? Because the same current that's in this guy splits between these two, right? So this current is the same as that current. So we can add either these two, that plus that, or this plus that, either one. It really doesn't matter. So let's look at the current that's going through R2 or R3, which is 0.25. Let's look at the current that's going through R4, which is 0.25. 0.25 plus 0.25 gives us a half. Or we said we could go this way. We can take current here, which is 0.25. We could add the current through R5 and RA. Sure enough, that equals 0.5. I think Kelly was a gross representation of the entire class. All right, so let's take a break. We'll come back and take the test. Just kidding. Okay. So what do we do? We filled in everything. I have to done my redraw, so let's go ahead and do that. Wait for a minute. Okay. So here's our givens, and I've pre-populated this table for everything. R1, we were given 28 volts. R2, we were given 20 ohms. R3, we were given the current through R3, which is 0.4 amps. R4, we were given 10 ohms. We were given RT total and voltage total. So pre-populated everything that we see there. So what's one thing we can calculate without even looking at our circuit at this point? Total current, right? So 50 volts divided by 50 ohms gives us 1 amp. So that means, if we look down this circuit, we have 1 amp current. We have 1 amp running through R1, 1 amp running through R4. So let's go ahead and populate that. 1 amp through R1, 1 amp through R4. But we can also make some assumptions too. If we've got 1 amp coming into this branch right here, and we're seeing 0.4 amps here, what else can we assume?
0.6 amps on R2.
R2 is 0.6. So we've got a few things to write in. We've got the voltage, the current through R1, current through R4, and we've got 0.6 amps on R2. Because we have the 0.4 amps provided. So, let's go ahead and make our calculations. What is the resistance of R1?
28 ohms.
28 divided by 1 is pretty much 28 ohms. All right, what is the voltage across R2?
12.
Yep, 0.6 times 20, 12 volts. Now R3, we're still potentially missing a piece of the pie there.
So I have 12 volts there also.
Exactly. It's in parallel with R3. R2 is seeing 12 volts. So there's R3's voltage. We divide that voltage by 0.4, what do we get? 30 ohms. And last but not least, we got R4, I times R, 10 volts. Now let's see if everything we've come to know and love does indeed work. If we add the voltage through R1 through R4 and either R2 or R3, so R1 is 28 volts, R2 is 12 volts, and R4 is 10. 28 plus 12 is 40, plus 10 is 50, does indeed equal that. And the equivalent should be the same for R3, R2 and R3 should be the same, so we see that. All right? We've got a total current of 1 amp going through R1. When it gets to this junction, the current's going to split. So the split currents between the two junctions, here and here, should add up to 1 amp. 0.6 plus 0.4 equals 1 amp. R4 should be seeing the same thing. So we're true there. Nice. So we see we can take different unknowns and work from the same solution. We've been working pretty much with a voltage and a resistive value for each of those. But if we've got various things and we remember these assumptions, or this, it's not just more than assumptions, these truths that holds true in these circuits, then we can apply them no matter what we're given and work our way back. Any questions on any specific types of circuits or anything we need to do? Because we will likely test in the morning. This. What now? Want to do another parallel and a parallel?
Yeah.
That's a beautiful way to finish up any day. So let's do that.
I suddenly feel myself coming down with something.
So parallel, and then a parallel. Make it a little different than what we're used to doing.
I'm gonna draw it.
We've got R1, R2, R3, R4, R5. All right? Yeah, group too big for our table. We'll stay here. Let's do 9 volts. Let's do 2 ohms. Let's do 6 ohms, 3 ohms, 6 ohms, and 2 ohms. There we go.
All right, this is showing up. I'll be there for any question.
Easy peasy, lemon squeezy.
Oh, man.
You have the voltage of all one and four, subtract that number from the total voltage, and it tells you what it's parallel to.
Okay. Thank you.
There's my missing scissors. another 2 or 3 minutes. We gotta make sure we got enough time to get through it. Yeah, tricked you a little bit. I messed with your head a little bit, messed with mine too. On this. But it's okay, it works out the same way. Should work out. It's okay.
That probably should be okay, but.
Let's go ahead.
Just trying to figure out R2 and 3.
All right. We've got this. We read through it. We've got R1. We've got the circuit splitting. We go through a parallel branch of R2 and R3. Then we go through R4 and we go through R5. So we've got to solve this parallel branch of this 6 ohm and 3 ohm first. So what's 6 and 3 ohms in 2 ohms here, right? So that puts us 2 ohms in parallel with 6 ohms, right? So what is 2 ohms in parallel with 6 ohms? 12 divided by 8 would indeed give us 1.5 ohms here. All right? So R1 is 2 ohms. R5 is 2 ohms. So 2 ohms plus 2 ohms plus 1.5 gives us what? 5.5 ohms. So what is 9 divided by 5.5? 1.64. 64. Yeah. All right. So we know that total current is 1.64. So that 1.64 is going through R1 as well as R5, and it's got, and it's going to split through this parallel branch, which has a parallel branch. So we can go ahead and populate R1 and R5. So what can we calculate?
Voltage drop.
Yeah, the voltage drop across R1 and R2. What is it for R1? 3.3. We round up. How about, through R5? 3.3. So if we're dropping 3.3 here, and we're dropping 3.3 here, that's 6.6. What are we measuring from here to here?
2.4.
2.4. So 6.6, 2.4, give or take a little bit of voltage in the hundred scale. So what is the voltage drop across R4? 2.4. Here's where it wasn't such a curveball, but y'all might have let it be. What's the voltage drop across R2?
2.4.
2.4. What is the voltage drop across R3?
2.4.
I tricked it because basically, without adding a series resistor here, basically, it's this right here. There's no difference in that draw and the draw I had before.
That's what I thought, but I was like, well, no, that's.
So I tricked it without meaning to trick it, but it really does apply some. So R2 is 6 ohms. And we solved it the same way. We solved it by doing the first two and doing the third. But they're all three saying 2.4. Now it's just a matter of applying Ohm's law. So what do we get here? 0.4. All right, what about here? Huh?
0.8.
How much?
0.8.
0.8. Okay, I said 1.8. I'm sorry. My ears were telling on me. What about the last one? 0.4, right? So if we add up 0.4 twice 0.8, we get close to the 1.64 that we had. So everything checks out there. So I tricked you without meaning to trick you. So in light of that, we'll work through one more. We'll have to work it together with the weight monitor. Since I cheated you out of a good problem, but really it wasn't a bad problem. It made us see that we do things differently just because of the way we annotate them on a piece of paper. So you wanted one that looked more like right here probably. My arch enemy. This is what you want. I lied. I didn't want the man to walk out of here and feel slighted. Now, this is R1, this is R2, R3.
Better watch it, because you can see going on toward that thing.
12 ohms. This is R5. Alright, there you go. So let's draw our chart. We'll go through our redraws.
Only what you're making now, but not me.
So we've got R1 is 5, R2 is 9, R3 is 12, R4 is right here, labeled 6, and R5 is 12. And we've got applied voltage of 20 volts. Let's do our redraws. R1, and we got a split. Wow, that's like Trump resistor drawing there.
I love you, Vulcan.
Not much better than we'll roll with. So,
Can you give you a sobriety test for a quick minute?
can't stand, I gotta fix it. Driving me crazy.
That good, but you just gotta take one.
Then,
Long time to figure it out.
alright, so this is R1, this is R2, R3, R4, R5. Then, we got this one. We'll label this one 1, 2. Come over and we'll draw.
Man, cow, he's got like 3 stuff.
2 cups. So this one is 3. Last but not least, I think I can squeeze it here. This one is 4. So let's do some quick labeling here. This is R1. This is R2, 3. This is R4. This is R5. This is R1. This is R2 through 4. This is R5. And last but not least, R1, R2 through 5. All right, so let's do some solving. The very first thing we have to do is solve that parallel within the parallel. So R2 and R3, that'd be 9 times 12 over 21. What do we get for the equivalent for that?
42.
So let's do the math. We'll do the reciprocal.
9.14.
So let's do the reciprocal. So we'll say 9 plus 12, 5.14, right? So the value for R2 and R3 is 5.14. Obviously, not written in Egyptian hieroglyphics. All right, so let's go ahead and populate. Well, we can't populate the chart yet. So R4 is 6 ohms. So we've got a total equivalent of R2 and R3 in series with R4 of what? Right, we add 5.14 to 6. So that puts this guy at 11.14 ohms. Now R5, we know the 12 ohms. So we got to do the parallel equivalent of those two. So I'm going to say 11.14 1 over x plus 12 1 over x. Whoops, I missed a key. 11.14 reciprocal plus 12 reciprocal equals reciprocal 5.78. So the equivalent of all of these is 5.78 ohms. Now R1 we know to be 5 ohms, right? So if we add those two together, that'll give us RT, correct? So 10.78 ohms. Now we can divide that into our 20 volts and get our total, correct? So we'll say 20 divided by 10.78 equals 1.86 basically. All right, so let's go back to our circuits. Here, we've got 1.86 amps going through R1. And really, that's the only place that we're gonna see full current through a single resistor, right? So let's write 1.86 amps there. Let's go ahead and do the math, lest we forget. So 5, I times R, 5 times 1.86, I didn't put my decimal. 5 times 1.86 equals 9.3. So we are dropping 9.3 volts across here. So what does that tell us is going to be across here? It'll be 20 volts minus 9.3, which will be 10.7 volts. Now, which of those resistors is seeing the full 10.7? R5. So let's go ahead and populate that. So if we've got voltage and we've got resistance, we can get the current through R5. So let's divide 10.7 divided by 12 gives us 0.89 pretty much. So 0.89. So let's look at this circuit. We know we've got 1.86 amps coming here, 0.89 amps is going this way. What's going the other way? What's going through this side? 1.86 coming in, 0.89 goes this way. What's going the other way? 1.86
.97.
minus 0.89, whoops, 1.86 minus 0.89 equals. Now we've got 0.97 amps starting here. It splits, but we know for a fact we've got 0.97 amps through this guy, and we've got the addition of these two that'll give us that. But we can go ahead and populate R4 with 0.97 amps. So if we've got I and we've got R, what can we get for R4?
You got 5.82 voltage drop.
Yep, 6 times 0.97. So times 6 equals 5.82. So we got 5.82 right there. So let's look across R5. We said we had 10.7. That means we've got 10.7 here. R4 is dropping 5.82 volts of 10.87 that's across here. What does that tell us about R2 and R3? Yeah, do the math. 10.7 minus 5.82 equals 4.88. So that means R2 and R3 are seeing 4.88. We divide 4.88 divided by 9, we'll get the current, which is 0.54. Back, bring it up. Clear 4.88 divided by 12, right? 0.41. So let's see if everything holds true. What we suspect. We should be able to add the voltage drop across R1 and the voltage drop across just R5 to get 20 volts, right? So R1 is 9.3 plus 10.7 gives us 20 volts. Now we can back up. We can also add the drop here and here and get it. So let's look. 9.3 plus 4.88 plus R4, which is 5.82, 8, 16, 0, 9, 10, 19. Where's the, oh, it's 20, yeah, that's the two. 20. Sorry, can't have. So spot on there too. So we proved that out, right? Now let's look at current. All right, the current going through R1 is 1.86 amps. I'll write it way down here so we can see it better. That is this current that's going through R1. So the current going through R4 should be equivalent if we add it to R5. So if we look at R4 and R5's current, and we add 0.97 and 0.89, we should add up, and looking at that, that's almost 100 plus almost 89, pretty close. In fact, it's dead on if we actually did the math. Or, if we take the current that's going through R5, again, so it'll show up a little better, and add it to the current that's going through R2 and R3, we should be able to get it. So 0.54, 0.41, and 0.89. 4 and 1 is 5, that's a 4, that's 10, that's 18, 1.84, we got 1.86, pretty darn close. Good. There's your parallel and a parallel, and I can't think of a better way to end the day. Test in the morning. I'll give you a true tech support call, talking about critical skills. This guy called a computer company and said, I got an issue, and this is true. I got an issue with my computer. Every time I flush the toilet, my computer reboots. I want y'all to have me an answer of how that could be possible tomorrow. That's a real life scenario.
Flush my toilet.
Every time I flush my toilet, my computer reboots. Tell us. Well, this is a true story. It is a true to life electrical story.
Okay. Yeah,
Where's
what
Mr.
we did.
Gates? He forgot to give me his sheet. I'm gonna look. Oh,
Well, you gonna do some more work. You're a working
I got
woman.
somebody.
I'm a working woman. Girl, I got 10 plates.
Critical thinking skill. Every time I flush my toilet, my computer reboots. Now, there is a logical explanation.
Chris, what's that?
Let me guess, every time we reach back
Every
flush
time I
toilet,
look at my phone, my computer reboots.
It's a true form electrical problem.
No, I'm bad
Every time
now.
the water pump come on? Every time the water pump come on for a little? It would, it shorted out a little? I just Googled it.
Yeah, it's a short.
Yep, what happened was he had a
Railing
wheel,
outside.
every time he flushed his toilet, the wheel
All
would
too
go
much
on.
current.
And his computer was under voltage, so he had to get an EPS put in his home.
Holy crap, Callie figured that out.
That is amazing.
Yeah, it is.
Just goes to show you.
It's a little scary. See, I heard the one where the dog